Last time we talked about how the sun, at the end of its life, will become a white dwarf star, an object made of carbon that resists its own gravity through the pressure of electron degeneracy. Remember all that stuff about the Pauli exclusion principle? So does that pressure have a limit? I mean, how much weight can electron degeneracy hold? Remember that the pressure of electron degeneracy is based upon the speed of the electrons as they fill the available energy levels. Remember also that nothing can move faster than the speed of light. And since energy is quantized, meaning it cannot be infinitely subdivided, there must be a final energy level that the electrons can fill before they would have to move faster than the speed of light. And it is this level that defines the pressure limit of electron degeneracy. That limit was discovered on the Orient Express in the year 1930 at the ripe old age of 20. A young fellow by the name of Subraman Chandrasekhar solved the formulas of general relativity that described the electron degeneracy pressure at the core of a white dwarf star. And he showed that that electron gas could only support a pressure equivalent to 1.44 times the mass of the sun. Indeed, Chandrasekhar won the Nobel Prize for this accomplishment. Since that time, this limit has been known as the Chandrasekhar limit. Stars often come in pairs, and sometimes those pairs can be pretty close to each other. So what would happen if a white dwarf star had a really close companion and it gradually stole mass from it? The mass of the white dwarf star would increase towards the Chandrasekhar limit. The infalling atoms would all enter the degenerate state, and the temperature would increase because the new electrons would be forced into higher and higher energy levels, moving faster and faster. And then, just before the Chandrasekhar limit was reached, the carbon atoms in the white dwarf star would begin to fuse into neon, magnesium, and sodium. This fusion releases a lot of extra heat. And in a normal gas, that heat would cause it to expand and thereby cool down. But this is a gas of degenerate electrons. And degenerate electrons don't expand when they get hotter. So the increase in heat causes the temperature to skyrocket. The increase in temperature greatly accelerates the speed at which the fusion reactions take place, therefore causing all of the carbon within the white dwarf star to fuse within a few seconds. The resultant output of energy is many billion times greater than a normal star and is sufficient to blow the white dwarf star apart at 6% the speed of light. Needless to say, this is a pretty big explosion. It's called a Type 1A supernova, and we don't want to be close to one. 50 light years would be a bit too close. Inside of 50 light years, we'd get a significant dose of gamma and X-rays, and that radiation would deplete our ozone layer. These events last for several weeks, and so the Earth would be broiled like a chicken on a rotisserie. Now, there ain't no point in letting the horses all run loose out of the barn, 'cause there's no white dwarf stars anywhere near us that can do us any harm. These events are impossibly rare. In fact, you'd be lucky to see one within 100,000 light years in your whole life. Indeed, in any given galaxy, you'll hardly get more than one per century. We haven't had one visible in our century for over 400 years. But if we did, and if it was within a couple of thousand light years, well, then it would be one heck of a show, because it would be visible during the day and you could read by the sucker at night. Correct me if I'm wrong, Spock, but aren't these events all very similar? Indeed, Captain. Since every Type 1A supernova is caused by a white dwarf star that encroaches upon the Chandrasekhar limit of 1.44 solar masses, they all erupt in a similar fashion, they all have similar power outputs, and follow similar light curves. And because they're all about the same brightness, we can tell how far away they are quite precisely. We have used this information to calculate the acceleration of the expansion of the universe. Cool. Consider for a moment the peculiar fact that we live inside a runaway expanding universe, adorned with Earth-sized diamonds that weigh more than the sun, that from time to time blow themselves to hell and gone. We truly all do live in the Twilight Zone.